So the next thing I want to talk about as an example of effective field theory is heavy quark effective theory. So again, what are our goals with this effective theory? We will see some new features showing up that we haven't seen before. We will find out what it means to take a Lagrangian that has labeled fields. We'll spend a little bit of time on symmetry because in this heavy quark effective theory, there's actually something called heavy quark symmetry, which is not apparent in QCD, but becomes apparent in this theory. And there's a trick known as using covariant representations in order to encode symmetry predictions. And it's a very powerful thing that's not special to this theory, but you could use it in general, and I want to teach it to you. So that's one thing we'll do. It's kind of like a spurion analysis, but a little bit more powerful. And finally, anomalous dimensions that are functions. There's something that will show up here, not just numbers. There's something called reparameterization of invariance. Which you can think of as a kind of symmetry that we'll talk about. And finally, if that list is not long enough, we'll add one more thing, which I hinted at. So I said when we talked about MS-bar that it wasn't a perfect scheme for doing things, that there were some limitations, and we'll come at the end of this chapter to what those limitations are. The limitations come from power-like scale separation, and that's related to something called renormalons. So we'll learn what a renormalon is and why it has something to do with the failure of MS-bar and how one can get around that failure and how one actually needs to get around that failure in some cases. Okay, so that's the list of goals in some ways in order of importance, actually. So when we think about heavy quark effective theory, you shouldn't think about it as just something that you would need to do if you wanted to do heavy quark physics. Because the idea of what we're doing here is much more general than that. The idea of what we're doing here is we're saying, take a heavy particle and think about what happens if I tickle it. And that heavy particle could be a heavy source in some theory. We'll talk about it in the context of them being heavy quarks, but you should really think of it as any heavy particle tickled by light particles. And what we really mean is that we want to study the heavy particle. And since we want to study it, we better not remove it from the theory. So we want to tickle it with light degrees of freedom, with light, small momentum transfer, but we don't want to integrate that particle out. So another way of saying this, if you don't want to think of it as a heavy particle, is that you have some source, and that source can be tickled and could wiggle, but it's sort of mostly just a static source, and then it could wiggle. And that's what this is an effective field theory for. So we'll talk about it in the context of heavy quark effective theory, and some of the things like heavy quark symmetry will be special to that theory. But more generally, the kind of approach we're taking is a more general thing. So what's heavy quark effective theory? So you have a heavy quark, and you have it sitting in a bound state, which is a meson. So that means it's surrounded by light degrees of freedom. One heavy quark, lots of light junk. In a quark model, you'd say it's a Q bar Q, a heavy quark capital Q and a light quark little q. like B bar D, which is the B0. But that's just a Quark model approximation for what the degrees of freedom are. And there's many more pairs of QQ bars and gluons that are really forming this hadronic state. So you'd like to be able to make model-independent predictions for that without having to worry about the fact that you're not parameterizing properly that stuff that you can't calculate. And you can do that using effective field theory. There's two scales in the problem. There's the size of this thing. The inverse size is of order lambda QCD. That's the hadronization scale. And that's a scale that's much less than the quark mass. So you're really just expanding in lambda QCD divided by MQ. That's what this effective theory will be. And what you want to describe are fluctuations of the heavy quark due to the light quarks. So you could think that this guy is so heavy, he just sits in the middle of the state, and he's static. And then he gets tickled by the light stuff that's flying and whizzing around. And that's a reasonable picture. So what we really want to do here is an example of top-down effective field theory again. So going back to our like integrating out heavy particles. But now we want to keep the heavy particles in the theory, not remove them. But still, we want to take a low energy limit of them. So that means that we have to take a low energy limit of QCD, which is ID slash minus MQ Q. And you can see that part of the problem here is that the MQ is upstairs, which makes taking the limit not completely obvious. In the case where we were doing the heavy bosons, we sort of saw that it was always in propagators, and we could just think of, since it's always their internal, we just expand. Here, we want to keep the Q in the theory, so we have to really think about how we take this limit. So let's start slowly and consider the propagator for a heavy quark. And we'll come back to the Lagrangian. And we'll consider it with some on-shell momentum. Which the on-shell, we'll consider an on-shell momentum to be parametrized in the following way. So if I have an on-shell momentum, I'll say that P is equal to MQV, so that P squared is equal to MQ squared, and this V is 1. So once I pull out the mass dimension MQ, the remaining thing I call V, and that's just some parameter which squares to 1 on shell. Now if I have kicks, which are from light degrees of freedom, then I don't have exactly on shell. So P mu is MQV, which is like the on shell piece, plus something small, K mu. And K mu is of order lambda QCD. So this is like saying the on shell piece plus the tickle. And if I want to construct the propagator, then the propagator is encoding off-shell, the off-shellness of the degree of freedom. It's 1 over the off-shellness. So it'll depend on the tickle. OK, so we could just take QCD propagator, just this, and just plug in that formula. When I square the P, there's MQ squared, which cancels this MQ squared. And there's some cross terms that don't get canceled. So there's one that comes from this, the dot product of the V dot M with the K term, that's this, and then there's the K squared term. So I have these. And then I can expand that. M is a positive quantity, so it doesn't change the sign of the I0. And if I expand in M, then the leading term looks like that. It's M independent. And then there's some order 1 over m terms, which I could also work out what they are. OK, so that we could expand, even though we don't a priori know how to expand the Lagrangian. We could also think about vertices in this theory. This is the propagator. What about vertices? And again, this is a top-down, so we can think about vertices in QCD and just think about, so if this is a heavy particle here, we could think about what would happen. How do we expand those? And there doesn't look like there's really anything going on here because there's nothing to expand. But because these things are heavy particles here, you realize from the propagator formula here that you're going to have 1 plus v slashes on each side of this guy. So for a propagator on each side, you can make a simplification. And that's because 1 plus v slash over 2, gamma mu 1 plus v slash over 2, after some Dirac algebra, is just v mu times 1 plus v slash over 2. So the gamma mu becomes a v mu. So the vertice, once you take that into account, is just minus ig ta v mu. And we can actually, even if we don't think about starting with the QCD Lagrangian, if this is our Feynman rule and that's our propagator, we can write down an effective theory for that that gives those Feynman rules. And that actually is the HQET Lagrangian. So sorry for going a little bit over, but I wanted to at least get a little bit into this. OK, so by construction this way, we can arrive at this Lagrangian. And next time I'll come back and I'll show you how we can really properly take this limit of the QCD Lagrangian to get the same thing. OK, but that is the HQET. The lowest order term of the HQET Lagrangian is this. So it's a linear v dot d coupling. V is a parameter, and so I've put it as a parameter on the fields. We'll see more why that was done next time. And there's a projection relation on the field. If I'm using a 4-component field and I have this projection relation, I could also write it in a 2-component notation, and then I wouldn't need that. But for 4-component notation, you do need that. We'll talk more about that next time, too.